So good morning all. Myself Shagun Patil. I am actually pursuing my master's from thermal engineering from College of Engineering Pune. Basically the title of my research is Improvement in the Hydraulic Performance of a Low Specific Speed Centrifugal Pump, Numerical Analysis. And yes, I know this is quite a different subject from all of yours. So it will, I think you will enjoy it actually. So I thank the International Conference of Mechanical Engineering and Applications to allow my this research. So basically, we will go through the abstract. So this current study analyzes a low specific speed centrifugal pump for a flow instability under part load conditions by experimental and numerical analysis. Three-dimensional steady state flow analysis is conducted over the actual impeller model having an outlet width of 44 mm. Numerical solutions are solved by Reynolds-averaged Navier-Stokes equations using the shear stress transport K omega turbulence model. Numerical solutions at different operating flow rates are compared with an experimental performance test. The numerical and experimental results agree well. Some methods have been developed to improve the stability of hydraulic performance. One of the methods, alternate impeller vane cutback, was adopted and tested successfully. In the investigated flow simulation, it was observed that reverse flow between the vane-to-vane passages caused pressure fluctuations under part load conditions. Impeller flow channels were blocked by the vortices forming in the vane passages. The reverse flow and the vortices in the impeller flow passages generates this instability in the flow inside the impeller and will affect the hydraulic performance of the pump. So I will quickly go through some fundamentals. So what is centrifugal pump? A centrifugal pump is a hydraulic machine which consists of a rotating vanes like impeller enclosed with a casing which imparts the energy to the fluid through the centrifugal force. The liquid is forced by the atmosphere, an external agency, into the rotating impeller. The impeller discharges the liquid at its periphery at a higher velocity. That's why impeller actually produces the kinetic energy, and this velocity energy is converted into pressure energy by the means of volute. Hence, I have shown here the energy conversion. If we are using a prime mover like electric motor, so the electric energy is converted into the mechanical energy by the help of shaft. Then the mechanical is converted to the kinetic energy by the help of impeller, and at last we get the pressure energy by the help of volute, that is casing. So because of this conversion of energy, there will be the energy losses. So mainly there are mechanical, volumetric, and head losses, and among them of all, head losses are more in a pump. So specific speed. Specific speed is actually an important criteria while designing a centrifugal pump. So it is the RPM to produce 1 meter cube second of flow at 1 meter head. Specific speed remains constant for all similar pumps. Here I have given it is a formula to obtain the specific speed. N represents the operating speed of the pump. Q represents the flow rate at the optimum best efficiency point, and H is the head at the best efficiency point of the pump. So depending upon the specific speed, the impeller shape of the centrifugal pump changes. So at the low specific speed, the impeller is radial. From 70 to 150, it is mixed flow, and above 170, it is axial flow. Not only the impeller shape also changes, but the performance characteristic, as you can see, it also gets changes. For this research, we will be considering the low specific speed, the radial pumps. So hydraulic design considerations. As we know, we have seen that the specific speed plays an important role. So the type of pump depends upon it. So after getting the type of pump, we go for the impeller hydraulic dimensions and the volute hydraulic dimensions. The main impeller hydraulic dimensions are the hub dia, the eye diameter, inlet width, the inlet outlet angle, outlet dia, outlet width, outlet blade angle, and the number of vanes. So for designing any kind of centrifugal pump, we should be familiar with the velocity triangles. So here is the representation of the velocity triangles at the inlet, trailing edge, and the leading edge of the impeller. This is the simpler way of representation of velocity triangles. So here the W1, you can see it is the inlet. This left side one is the inlet velocity triangle. The right one is the outlet velocity triangle. So W represents the relative velocity. The C represents the absolute velocity, and U1 represents the peripheral velocity. So the performance characteristics, for if we have a duty point, like we call at we have a flow rate and a head, so we should select a pump according to the performance characteristics of that pump. So when the flow rate of a pump varies with the head, the power consumption and the efficiency changes too. So plotting these quantities with respect to the flow rate, we can obtain the performance characteristics. So at a certain flow rate, the pump efficiency, as I mentioned earlier, is maximum. So this point is called a best efficiency point. So the pump is basically designed at this point only. So the problem statement of my paper was like, in pump standard API 610, the pumps are operated in parallel conditions mostly. So as we have seen here, the pump as we approach to the shutoff head is actually the head at the zero flow rate. So as we approach to the shutoff head, the curve rises, the head curve rises. So but in low specific speed pumps where the flow rate is less and the head is high, so it does not happen. So rather there is a peak head at some capacity, and from that point the head falls constantly to the shutoff. Such pump is known as a drooping curve. So drooping curve is a type of unstable performance characteristic found in centrifugal pumps. So what is a drooping curve? So this left one figure is the stable curve. So we can see here, this is the pump curve in blue curve, and the red curve is a system curve. The system curve is a pipe frictional resistance of that pumping system. So wherever these two curves meet, at that intersection point, the pump is going to be operated. So this is the stable one. Now what is the drooping curve? So whenever pump develops a certain head at more than one flow rate, we call this condition as an unstable performance characteristic. So here are two different flow rates, but the head at these flow rates is same. So there it generates a hump actually, you can see. So this is an unstable zone in which we can't predict where the pump is actually operating. So what are its causes? So the relation between the flow rate and the theoretical head, that is also called as Euler's head, is expressed as a straight line. So the impeller, the backward swept impellers have generally outlet blade angle less than 90 degree. So their QH curve is steadily rising towards the shutoff. So in actual pump, the value of this theoretical head at any given flow rate is reduced by a magnitude called HR. This is a head reduction, which is mainly due to the combination of factors like slip, hydraulic losses, pre-rotation at the inlet, then rotating stall and recirculations. So we will see that we have actually, I have actually investigated this in my research. So what factors were influencing this, what factors were causing this unstableness in the flow. So the magnitude of HR and the manner in which it varies with the flow rate are among the main factors which determine the QH curve. So there were some methods in the literature which I have gone through and I have studied thoroughly. So the first one was cutting back every alternative vane. So this can only happen if the number of vanes are in even number. Then the second one was partial cutback of vanes at exit from the impeller at the inclined plane. So this modification removes part of the discharge recirculation zone. A reduction in hydrodynamic losses takes place and results in an increase of a head at reduced flow near the shutoff region. And the angle shown in the figure, it is recommended that it should remain 12 degrees only for the best results. Then the slotting of the vanes at the crown of the impeller. This is similar to the modification as we have seen. Its performance is same with the inclined plane as mentioned before, cutting back the peripheral portion of the vanes at the entry. This modification steepens the curve, but it is not recommended in case when vane loading at the shroud is high. Yeah, so the pump which we investigated for this research was having a specific speed of 30.42. Then the impeller was a closed channel shrouded type. So the pump was designed for the duty parameters of flow rate of 1050 meter cube per hour, and the head was 76 meters, and the operating speed of it was 1450 RPM. So the main hydraulic dimensions of impeller and volute are in the table. So this was the actual impeller on which we had investigated. This is the test setup where we tested the actual pump. So in test setup, we connected the pump to a 15,000 liters flooded tank. Then it was 300 NB suction pipe and 250 delivery pipe. The flow was regulated by the sluice valves, and the readings were taken from the shutoff head to slightly ahead of the desired duty point. The pump was, as this pump is very big, so due to some power restrictions, we tested at a reduced speed by the help of VFD, variable frequency drive. Then for reduced speed, we used affinity laws to convert these flow, head, and power readings to the full load speed. So flow was measured by the electromagnetic flow meter. For pressure measurement at the delivery side, we used Bourdon tube pressure gauge. For suction pressure measurement, we used U-tube manometer. And for to measure the speed of the pump, we used the tachometer. And both the impellers. So basically, at first, we got this impeller in unbalanced mode. So we modified the impeller with one of the methods mentioned before. And then we retested in the same volute only. So all these performance testing was done with the compliance of ISO 9906. So for efficiency calculations, we needed some readings as mentioned, like rate of flow was taken from the electromagnetic flow meter, power was taken directly from the control panel, watt meter, speed was measured by tachometer. So these are the calculations which we used to obtain the pump efficiency. Affinity laws, which I mentioned before, were used to convert the parameters, fluid parameters, to the full RPM, full speed. Then we conducted a numerical analysis to investigate what was the cause for this unstable performance in the hydraulic nature. So for that purpose, ANSYS was used actually. So it has three elements basically in CFD: pre-processor, solver, and post-processor. So in pre-processor input of the flow problem, we generated the geometry. Then computational domain, like fluid volume was extracted, grid generation, the mesh generation was done, definition of the fluid properties and boundary conditions were given to the problem. Then for solver we used ANSYS CFX. In that, approximation of unknown variables was done. Then discretization by substitution methods in governing flow equations, like energy equation, Navier-Stokes equation, and species equation was calculated. Then large amount of data is obtained at this step. In post-processor method, the most important step was to analyze the data, and the graphical representation and pressure contours were obtained. So in pre-processing model, the 3D model of the impeller was generated in cryoparametric, and using ANSYS space claim, the fluid volume of it was extracted. In meshing, in this simulation, structural tetrahedral mesh is generated for the fluid volume. Suitable wall refinement has been done at the blade, shroud, and the hub wall. Mesh independence test was carried out to select proper number of meshing elements. 4 meshes were performed and their meshing elements were compared. The comparison between these sets is done by the help of relative pump head. The mesh independence test illustrates that a mesh of 8,09,778 meshing elements is the acceptable range between the solution accuracy requirement and the computer resources which were available with us. This table shows the actual independence test which we conducted. So for CFD solver, ANSYS CFX 19.2 was used. Water at 30 degrees Celsius as a fluid is selected. Then the K omega shear stress transport turbulence model is selected to check the instability characteristics at part load conditions in the pump, such as flow separation, rotating stall, and reverse flow. A rotational coordinate system is set for the area of pump impeller. The boundary template of pressure, total inlet, and mass flow outlet is used. According to the operating conditions, the mass flow rate is assigned to the impeller outlet, while the total pressure boundary condition is assigned to the impeller inlet. All remaining solid walls are assigned to no slip boundary conditions. In the solver control, the residuals were set to 0.4 times 0.1. For convergence of the problem, a maximum number of iterations were set to 250 iterations. So this is the table where you can see the solver boundary conditions and solver control boundary conditions. So in post-processing model, CFD post was used. So basically it it operates on a vertex-based set of data, that is variable which are primarily stored in the vertices of the numerical mesh. The results from CFD are typically visualized through post-processing software closely related to pre-processing and simulation software. After getting results in simulation stage, next step is to analyze those results, use the available methods such as vector plots, contour plots, data curves, and streamlines to achieve this. Results and discussions. So in experimental results, both performance tests were conducted for constant flow rates at 0, 400, 885, 980, and 1050 and 1215 meter cube per hour. First, the original impeller was tested and a highly unstable curve was observed. So basically this red one is the hump which we were getting. This is an unstable zone. So this is after the observing of pre-rotation and suction and rotating stall in the impeller passages. The same impeller was modified by cutting the alternate vanes partially at 12 degree and also cutting back a peripheral portion of the vane at the entry was done. A comparison of experimental performance characteristic has done for both original and modified impellers. So this was the red curve. It is the original impeller, and in dashed line curve, it is the modified impeller. So basically, after doing the modification, the curve has actually somewhat steepened, and the hump has been decreased with in reduction to, as I think, 60 to 70%. In numerical results, the pump characteristic curve was generated by solving the fluid domain for different flow rates. Similarly to the experimental analysis, the pump has instability in the head when operated at flow rates at 360 meter cube per hour and 950 meter cube per hour. And present simulation can be used to show the flow instability criterion in the pump. At the part load conditions, Q is equal to 0.5 of Q BEP and 0.6 of Q BEP, and Q is equal to 0.65 to 0.72 of BEP. The fluctuation in the pressure is high. So this is the part load condition actually. Furthermore, we can observe that the best efficiency flow rate of the pump is nearly same as the design flow rate. So likewise, like before, this was the experimentally generated curve, and this was the numerically analyzed curve. So the nature of the curve was followed in both the cases. So after investigating the impeller analysis, we got to know that this velocity vectors and streamlines were generated in the simulation to observe the fluid behavior inside the impeller under different operating conditions. Following figures, like this figure shows the velocity vectors in the passages. So the first figure is for 0.5 BEP, the second one is for 0.62. In this case, we can see where some vortices are formed in the vane-to-vane passages. So at part load at 0.5 QBP, the maximum vortices were formed. As the flow was increasing, the vortices were reducing actually. So for 0.8, there was somewhat recirculation in 2 to 3 passages, you can see, and 2 to 3 passages, the streamline flow can be observed. And at the Q best efficiency point, the flow was totally streamlined. At the 0.5 QBEP, the reverse flow is observed in the impeller vane-to-vane passages. We can observe that as the capacity increases, the vorticity decreases. There is a certain amount of energy loss in the impeller passage due to reverse flow and vortices. These three operating flow rates are situated in the region where the flow instability is observed. The operating flow rate, that is the part load, is start of the flow instability in the pump. Thus, the vortices and reverse flow occurred at the entry of the impeller, resulting in the flow instability criterion. At the best efficiency point, the streamlines between the vane passages are generally smooth and no stalls are formed. With a decrease in flow coefficient, rotating stall develop in the passages of the impeller. Interestingly, two vane-to-vane passages are blocked by vortices at Q is equal to 850 meter cube per hour, whereas 5 vane-to-vane passages were blocked at Q 650 meter cube per hour, and 7 vane-to-vane passages were blocked at part load, that is 525 meter cube per hour. These factors cause tremendous losses in energy. So the rotating stall, what we observed, was occurring into the passage of impeller vanes as the flow rate was decreasing. The type of vortices depend on the number of blades. If the number of blade is even, then the stall will be performed in every alternate blade to blade passages. And if the number of vanes are odd, stall would form abruptly. Head drop over a performance curve can occur due to this phenomenon of rotating stall. So comparison of experimental and numerical analysis. Instability in hydraulic performance was observed in experimental results after the performance test of the pump. The hydraulic performance was largely affected by the abnormal flow behavior. After the numerical analysis, it was observed that this abnormal behavior was mainly due to reverse flow at the inlet of the impeller, formation of vortices in the blade-to-blade passages of the impeller, and okay. So comparison, a method was opted to improve the hydraulic performance of the impeller, and it was observed that instability was not fully vanished, but it was decreased to a certain level. After the modifications, the alternate 4 impeller outlet angle was changed to 23 from 32 degrees, and vane inlet angle of all vanes was changed to 20 from 25. By the use of design software called CF Turbo, impeller main dimensions were calculated. Blade angles were close enough to the actual blade angles. The calculated angles were 20 degree and 16 degree. Number of vanes calculated were 5 vanes, which on actual impeller there were 8 number of vanes. So basically this all caused because of the number of vanes also, and the angle of blades. So this is the superimposition of the experimental curve and the analytical curve through the numerical analysis. So in this case, we can see at the 0.5 of QBEP, at the part load, the maximum instability in the performance was there. But as we increase the flow rate at best efficiency point, it was steepening at the best efficiency point. So the conclusions, the above numerical procedure which we held for observing the instability in centrifugal pumps, this can also predict the hydraulic performance of the pump at part load and full load conditions. The energy loss in the impeller is mainly due to reverse flow at inlet and formation of vortices or rotating stall in blade to blade passages. These vortices block the vane passages and result in head loss. Blade curvature, blade angles, and number of blades play an important role for stable performance characteristics. Generally, outlet blade angle should be in between 20 to 25 degree for low specific speed centrifugal pumps. Instability was reduced to 70% by cutting back the alternate vanes of impeller and cutting back the peripheral portion of the vane entry. So yes, these were the references through which I went throughout my study. Thank you. If there are any questions, we can go through it.